Well, hello everyone and welcome to our calculus notes for section 4.5, integration by substitution. Now the point of this lesson is we're going to be able to integrate functions that are composite. And so it's really going to be taking a look at the chain rule for derivatives and then doing that in reverse. So the big key here is, can you find the derivative as the integrand, and is that part of the chain rule? And so we're going to be looking first at pattern recognition. So first off, let's take a look at the chain rule for differentiation that we've done before. So here we have the derivative with respect to x, and if you look carefully here, we have an outer function. We're going to call that capital F. And then we're also going to have an inner function. We're going to call that g at x. Okay. Now, when we took the derivative of this, notice what we got was this capital F prime. And so this was the derivative of the outer function. And notice we kept it at the inner function. And then the chain rule was applied by taking the derivative of that inner function and multiplying. All right, so that is the chain rule for derivatives. So what we're going to do now is take a look at finding the antiderivative of a composite function. So when we look at this, what we've learned is that if we were to integrate both sides, let's say, with respect to x, all right, look what's going to happen here. We know the integral undoes the derivative, and so this is basically gone here. And so what we have here is the integral, or antiderivative, of capital F prime at g at x times g prime at x with respect to x is that capital F antiderivative at g at x. So what we're looking for when we look for the antiderivative of a composite function, okay, we have some sort of outer function, f. It's going to be at some sort of inner function. And the trick here is that to be able to integrate this, this has to be the derivative. This has to be the derivative. And so what we have to have is the chain rule, where we have the derivative of the inner function as part of the integrand. Okay? Now, when that happens, it all kind of gets packaged back up as the antiderivative of the outer function. So this is the antiderivative of the outer function. And it's still going to be at the inner function. That never changes. And then the only difference here is we're going to have a constant of integration that we're used to having when we find these antiderivatives. All right. So the integrand consists of an outside function f, an inside function g, and the derivative of that inside function g prime at x inside the integrand. So let's go ahead and recognize this pattern and see if we can find some of these antiderivatives. Okay, so in example 1, we have the antiderivative, or the indefinite integral, of x squared plus 1 quantity raised to the power of 2 times 2x dx. So a couple things that are going to alert us to this idea of the pattern is, one, we're going to have composite functions, and we're also going to have some sort of multiplication of two different functions. So in this case, I'm going to let the outer function be something squared. And what that does is it kind of makes my inner function, okay, be this x squared plus 1. And so what we're looking for now is the derivative of that inner function right here. Okay, so another way that we can think about this is that we could let that inner function be some other function like g at x. Okay, and so we'll just call that x squared plus 1. And then when I find the derivative of that, g prime at x would be 2x. And we're going to do something special here. We're going to put a dx. So whenever we do this, let's go ahead and just put a dx there, recognizing that it is the chain rule. The derivative of x is kind of dx there. Okay, so now when you look for this, what you're going to find is our outer function, but we have an inner function there, and then we have the derivative of the inner. All right, now when this happens, we can go straight to the antiderivative of the outer function. Okay, and so the outer function was something squared. So what it's going to be something cubed over 3. All right, because we raise the power 1 and we divide by that new power. Now the inner function doesn't change. So this is just going to be x squared plus 1. And remember, because we're doing an antiderivative, the derivative of the inner function, that 2x dx, is re-encapsulated within that inside function, the x squared plus 1 there. Now all we have to do left is add c. And so this right here would be our antiderivative. All right, let's try it for letter B. All right, so here we have the antiderivative of 6x divided by quantity 3x squared plus 1 raised to the third power. Now, before we get started, we are going to rewrite this so it's not rational. Instead, we're going to change the denominator to be a negative exponent. So this is going to be 3x squared plus 1, and that's going to be to the negative third power, and then with respect to x. All right. So we can see here there's kind of a multiplication. There is a composite function. And so we need to identify the outer function, which will be something to the negative third power. We need to identify the inner function, which is going to be 3x squared plus 1. Okay. Now what we have to ensure is that we have the derivative of the inner function also in the integrand. So if we let g at x, the inner function, be 3x squared plus 1, then the derivative of that, g prime at x, is going to be 6x dx. And sure enough, if we look in the integrand, we have 6x dx. So the derivative of the inner function is there. So what we need to do when we take this antiderivative, okay, is just focus on the outer function first. So the outer function is something to the negative third, which means we're going to add 1 to that exponent, divide by the new exponent, and then we're going to keep this at the inner function of 3x squared plus 1. And then finally, just plus c. Now we do want to rewrite this, and so we do have a negative exponent, which is going to move into the denominator, become positive, and then we also have a negative 2, so the overall answer is going to be negative here. So all in all, I'm going to get negative, and then 1 divided by 2 times the quantity 3x squared plus 1 raised to the second power, and plus c. All right, so we're going to try to get a little bit quicker at recognizing this, okay? So we don't need to actually rewrite everything every single time. Let's look at letter C. What I see here is an outer function, so something raised to the third power. I see an inner function of x squared minus 1, and what I'm looking for is, do I have the derivative with respect to x of that inner function? And the derivative of x squared minus 1 is my 2x. And so everything is there, and it's exactly in this pattern. And so we can go straight to our answer now of raising the outer function power by 1 to the fourth, dividing by the new power, and then keeping that inner function the same, x squared minus 1, and including the constant of integration. All right. So let's try it with letter D and see if we can do the same type of idea here. All right, so first off, I do want to rewrite this, getting rid of the radical. So we'll have 12x cubed, and then quantity 3x to the fourth minus 3 raised to the 1/2 power, and dx. All right, so looking at this, looks like I have a composite, something raised to the 1/2. I do have an inner function here, 3x to the fourth minus 3. And what I'm going to try to see is, what is the derivative of 3x to the fourth minus 3? And you'll see that it is 12x cubed. We got our dx in there. And so when we go to integrate this, we're going to raise the outer function by 1. Okay, so 1/2 is going to go up to 3/2. Now we can divide by 3/2, probably easier if we just multiply by 2/3. And then we're going to keep that inner function the same, 3x to the 4th minus 3, and add our constant of integration. Okay? So again, you just have to find that inner function. You just have to verify that, yes, indeed, that is the derivative of the inner function, and then you can just integrate the outer function at the inner function. All right, so do we need to clean anything up here? Nope, this looks pretty good to me. All right, so that is finding antiderivatives of composite functions just using a pattern recognition. All right, next we're going to look at the idea of dividing and multiplying by a constant. So many integrands contain the variable part of g prime at x, but are missing the constant multiple. Okay, so they have the right variable to the right power, but the constant multiple is off a little bit. Now, if you can determine what that constant multiple should be, you can multiply on the inside of the integrand and divide on the outside, and it will balance everything out, thus giving you the derivative in the inside. So we're going to multiply and divide by a constant in order to find these definite integrals using substitution. All right, so let's look at letter A here. So what you do want to notice first is that this is a composite function, some function to the second power, and we do have an outer part that's kind of being multiplied there. Now the inner part here is the x squared plus 1. And we're going to go back and just rewrite this here. So g at x is equal to x squared plus 1. That's the inner function. Now we do want to find that derivative. And what we're going to see is we get 2x and then the dx. Now, if you look back into the function, I see the x here and I see the x here, and of course the dx and the dx. So you have to think, what are we missing? Well, we have the variable part of the derivative. We're just missing the constant multiple. And so that 2, we're going to need to multiply by 2, and now we have it. Okay, but what we just did was multiply the entire thing by 2, and so in order to balance this, we're actually going to have to multiply by 1/2 on the outside. So now that we have the entire derivative of the inner function in the integrand, now we can just do the antiderivative of the outer part, something squared. So we do have the something to the third power over 3. Okay, the g prime at x kind of gets pulled back into that inner function. So we have x squared plus 1. And now we can't forget the 1/2 that we had to multiply on the outside to make this thing work. So we're just going to apply that now at the end. And so our final answer is going to be x squared plus 1 quantity raised to the third power over 6 and plus c. Okay, so don't forget about that constant of integration. All right, so let's give letter B a try here. So it does look like I have a composite, so something raised to the second power. My inner function is the x cubed plus 1, and so we'll call that g at x. And we want to find that derivative, so g prime at x is going to be 3x squared and dx. And what we're going to notice is we have the x squared part and we have the dx, but what we're missing is the 3. So what we're going to do is multiply on the inside by 3 and on the outside by the reciprocal 1/3 to balance it out. All right, now we have the entire derivative of the inner function represented. And when we go to solve this, we have that constant multiple, the 1/3, which balanced everything. And now we're going to raise the outer function by 1, divide by the new exponent. We're going to keep the inner function the same. And that already has the part that has the g prime of x for us when we do take that derivative. And we'll add that constant of integration. So we'll just simplify here. And we're going to get x cubed plus 1, that quantity to the third power. And then divided by 3 times 3 is 9, and plus c. All right, so those examples demonstrate how you can multiply on the inner and the outer of the integral so that you can get the complete derivative on the inside. All right, in this next section, we're actually going to take a look at the same process, except instead of using g at x and g prime at x, we're actually going to use something called u and du. And we're going to just completely change the variable out from x and rewrite everything. And maybe this will be a little bit easier for some of you, rather than doing the multiplying and dividing by a constant. So I just want to show you this method as well. So using substitution, if u equals g at x, so u is going to be that inner part, and then du is going to be g prime at x, then what we can do, instead of having f at g at x times g prime at x dx, which is what we were dealing with before, we're going to have a little bit simpler look, and it's just going to be f at u du, and then we just have the antiderivative of f at u plus c. So essentially it's the same thing, but when you're doing these steps, it's going to feel a little bit different. Okay, and this is actually a little more methodical and step by step. And so here are some directions on how to do this. Choose a substitution, u equals g at x. So this could be the inner part of the composite function. We want to compute du, and that's going to be g prime at x times dx. Then we want to rewrite the integral in terms of u and du only. After that, you find the resulting integral in terms of u. Substitute g at x back in for u at the very end, and then you can always check your work by differentiating. So let me show you what we mean by that. So when I'm looking at this, I see the square root of 2x minus 1. Now what you're going to do is first let u be the inner part of the composite function. Okay? And so in this case, u will equal 2x minus 1. All right, so that's the inside part. Now what we want to do is find du. And what that is really just the derivative of 2x minus 1. And so the derivative of 2x minus 1 is 2. And because the variable is x, we have a dx here. All right, now here is kind of the tricky part. What we want to do is actually solve for dx. Okay, so to solve for dx, what I want to do is divide by 2. And notice what we get here now is that dx is equal to du over 2. What we're going to do now is actually substitution. Okay, so instead of dx, I'm going to write du over 2. And instead of the 2x minus 1, I'm actually just going to write u. All right, so this is going to become your change of variable here. So we'll have the definite integral of the square root of, well, not 2x minus 1. We're going to change that to be u. And instead of dx, we're actually going to write du over 2. Okay. Now, from here, we do want to rewrite this a little bit. So the du over 2, the divided by 2 is a constant multiple, and that can come out in front of the integral. And then this is going to be to the 1/2 power. And then we'll be left with a du here. Now, the inner function, we're just going to leave as u. So when you look at it this way, we have u to the 1/2 times du. So this no longer really looks like a composite function. Okay, it looks kind of like if we had x to the 1/2 dx. And so we're able to actually integrate this just like we had done before with an antiderivative. So we have the 1/2 on the outer part, and then we think the antiderivative of u to the 1/2 will be u to the 3/2, and instead of dividing by 3/2, we're actually going to multiply by 2/3, and then we'll have a plus c. So we don't really have to think in terms of the outer function and the inner function anymore, because we substituted the inner function just as one single variable. From this point, we can go ahead and simplify. So the 2's will cancel, and we're left with u to the 3/2 over 3 plus c. Now, at this point, this is the antiderivative, but it's in terms of u, and because the original question was in terms of x, we do want to back substitute for u, okay, whatever u was. Oh, see, it was right over here. U was 2x minus 1. And so we're going to back substitute now back in for u. And so this is going to become 2x minus 1 raised to the 3/2 power over 3 plus c. All right, so just a little different tweak on how we do it. And what you'll notice is that when we multiplied and divided by that constant, that kind of gets taken care of right here when you're solving for dx. Okay, so this is just a different way of doing what we had previously done, but in a lot of respects, this is a lot cleaner and will actually help along the way as we get into some more difficult problems. So let's give this another try. Make sure we can do this. All right, so I see I have a composite function here, and we have an inner function. So I am going to let u equal that inner function. And what I want to do is find du, which in this case will be 3 dx. Now, if we just followed the same steps blindly, what we would do is solve for dx. So we divide by 3. Okay, and you can see that dx is now du over 3. And what we're going to do is go ahead and just do a substitution now. Okay, so we have the antiderivative. We still have the 3. We still have something to the 4th power. Now, the 3x minus 1 is going to get replaced with u. And then dx is going to get replaced with du over 3. Now, before we go ahead and take the antiderivative, we need to simplify. And what you're going to see here is that these 3's are going to cancel. All right, and so we're going to be left with the antiderivative of u to the 4th du. All right, at this point, we can go ahead and take that antiderivative, and so it will be u to the 5th over 5 plus c. And now we want to back substitute for u. So we're going to rewrite that as 3x minus 1. And that'll be raised to the 5th power over 5 plus c. Now, some of you may have noticed when we were doing this that du was equal to 3 dx, and you can see 3 dx right there. So why don't we just use pattern recognition? Well, if you see it and you actually recognize the pattern, then by all means, go ahead and use that. But if you don't want to even think about the pattern recognition, what I'm saying is you can always use this u substitution, and if it works, great. It's always going to get you to the right answer. All right, let's try this one more example here. All right, so when I see the composite portion in the denominator, what I'm going to do is rewrite this so we have a negative exponent. And so this will be x cubed plus 1 to the negative 2nd power dx. So my inner portion is the x cubed plus 1, so I'm going to let u equal x cubed plus 1. I'm going to find du, and that's going to be 3x squared dx. I'm going to solve for dx, so I'm going to divide by 3x squared. And that will cancel there. And so what I see here is that dx is equal to du over 3x squared. And we're going to end up substituting that in right there for that dx. So I'm going to get x squared times, well, instead of x cubed plus 1, I'm going to write u. That'll be the negative 2nd power. And instead of dx, I'm going to actually write du over 3x squared. Now we're going to go ahead and simplify this, and what you're going to see is the x squared and that x squared cancel, and we're left with du over 3. So when I look at this, I have a 1/3 times the antiderivative of u to the negative 2 du. Now we can go ahead and just find that antiderivative. So it'll be u to the negative 1st power over negative 1 plus c. And now we'll simplify. So this becomes times negative 1 over u, and then plus c. And finally, we're going to back substitute in for u. And so I get 1/3, negative 1/3 And instead of u, I'm going to have x cubed plus 1. And so I get negative 1 over 3 x cubed plus 3. And finally plus c. All right, that's everything. And good luck with this u substitution.